Well, thank you very much for that kind invite. I just wish you'd organized a bit better weather. You know, even though I'm from the Ottawa Valley, I've forgotten all about that weather. You know, us Vancouverites are pretty soft.
This is good weather.
Oh dear, when's my plane? Okay, well, you know, thank you for that kind invitation. And you know, first of all, before I start, I just want to give special acknowledgement to Ron Britton. Ron was my partner who helped start FFPX. We worked together for about 20 years, and he was one of the key people behind identifying and moving forward on this fairly unique style of nickel deposit. So as you know, this was an invite with the CIM, the CIM Foundation, provide funding and so on to help this happen. But it's also actually part of the honorary distinguished lecture series for the Canadian Mining Hall of Fame. They are both, you know, linked together. So there's going to be questions on this afterwards. So I hope you're fast readers. So I'll show you this diagram first, and then I will come back to it. This is just to give you an overview. Look at the scale bar here. Big system. This is the ultramafic, the ophiolite that I'll detail more of later. And these are the occurrences of Awaruite, which I'll go into in quite a bit of detail. And in particular, I'll focus, on the Baptiste deposit down here, which is the one with by far the most work on it. So, what is Awaruite? You know, I'll be honest, before I started working here, I'd never even heard of the mineral. And I've met people who worked in nickel for a very long time who'd never heard of it either. So it's a nickel iron alloy. It's a naturally occurring one. It's 75% nickel, 25% iron. And it can have a few trace elements. It can contain some copper and cobalt in like the 1% range. It's always very strongly associated with magnetite. The quantity of magnetite normally greatly exceeds the Awaruite. And it is very strongly magnetic, ferromagnetic, more strongly magnetic than magnetite, and which really helps us on the separation side. And it's quite dense, you know, 8.2, which is magnetite's about 4. So, you know, it gives us a method for physically separating them. Awaruite's actually much more common around the world than I had ever imagined, and I think most anybody would have imagined. It doesn't get much press, but where it occurs around the world, it's often associated with these small chromite lenses and deposits, which tend to be of a little an economic interest. And I should also point out that it's an isomorphous series. The nickel content can change from a low of 60 to a high of 80. So at the Decar district, the subject of this talk, this occurs in serpentinized ophiolites. And this is the economic focus. It's widely spread, widely disseminated over a big area that gives us a bulk tonnage open pit target. And that's exclusively what we're focused on. We've looked at quite a few other occurrences around the world, and we've read the literature of where they exist. Awaruite was actually first discovered in Awara Bay. It's a Maori word from mineral sands in New Zealand. It can occur in oceanic ultramafics. In Quebec, in the Dumont-Sill, there is Awaruite there, but a lot more sulfides than Awaruite, and there's these very odd Josephinite things. It was written up a lot in the 70s when it was first discovered. Big nuggets, almost head size, but certainly fist size and smaller. This peculiar association of Awaruite and andesite, garnet, diopside, sulfides, and taenite, which is just 50-50 nickel iron. And people have debated whether it was a mantle plume or whatever. Interesting to look at. Nice samples that stick to a magnet, but of not much economic interest. So, how does it form? This is the oxygen sulfur stability field, and a couple of things to note here. The oxygen fugacity is really low, and the sulfur fugacity is pretty low. And the Awaruite field is really quite restricted down here. And if you move out of that field very far at all, certainly if there's much sulfur, you get sulfides. If there's much oxygen at all, you get hazelwoodite and millerite, so other sulfides with a higher nickel sulfur ratio. And it's very important then from the generation of this that you're in this fairly unique environment, which apparently isn't found in a lot of places around the world. Looking at the mineral assemblage we have here, antigerite, fosterite, brucite, and then with trace amounts of magnetite and awaruite. The temperature of formation, would appear to be in the 3 to 450 range, and that temperature is the kind of temperature that can be produced just by the hydrothermal reaction, just by the exothermic reaction of the formation of serpentine or quite low-grade metamorphism. So the host rock at Decar are ophiolites. They are prograde metaserpentinites. And what happens just during serpentinization, if the olivine gradually gets used up, and as soon as the olivine's gone, the fugacity of oxygen will tend to climb very, very rapidly. And so move very quickly out of the Awaruite field. So the Awaruite without sulfides present tend to be in only partially serpentinized peridotites. They can be 95%, but there's often still some relict olivine left. Otherwise, you move into the sulfide field, and the mixture of Awaruite and sulfide is metallurgically quite a lot more difficult than just Awaruite on its own. So we've avoided that system, and no one else in the world has tried to tackle that, except in Dumont, which is quite a different beast, and they have a hugely complex metallurgical circuit. We also feel that shearing, fracturing, any form of porosity, which maintains that porosity over a big area, is important to the formation of Awaruite over the size of areas that we're looking at. So ophiolites, there's probably some people in this room who are pretty experts in ophiolites. The column on the left is from Oman. that's probably the best preserved and biggest ophiolite in the world. The column on the right is from the Cache Creek terrain, which I'll show you a map of in a moment. And just to compare the two, a couple of things to note here. This ultramafic section is up to like 7 kilometers, possibly even thicker. We don't know how thick the ophiolite is at Decar. We can't see the bottom of it, but it's certainly at least three kilometers, which we can see, and all our holes are still in the ophiolite, and the Awaruite occurs in this section here. So moving on to a bit of a geographic location, all the colored material here is the Cache Creek here and down there. For those of you who don't know the geography of BC, Fort St. James, Fort Prince George is over there, Prince Rupert's here. That's about the exact center line of BC. So there's as much north of there as there is south. Decar is down here, and then these Clo, Lutain, Orca whale, and Mitch are other occurrences of Awaruite, part of the same system, but it's Decar actually fortuitously was the first one that we found, and it's turned out to be by far the most important to date. So the evolution of the Cache Creek terrain, going from early Cretaceous to Eocene, it was moving west. The continent was being moving east. The continent was being subducted underneath, and you got this terrain broken up into a number of fragments that are quite complex, but the Decar on ophiolite, which sits down here. Sorry, I keep hitting the wrong one here. Down at the bottom has been preserved quite reasonably well. So if you look at this in a bit more detail, that's a blow up of part of the Cache Creek terrain. And if you take a cross section through there, and Decar and the different prospects within there occur across that line, this is a conceptual model of what it looked like as constructed by the BC Geological Survey. Serpentinization, there's probably people in this room who, again, know more about it than I do, but very different. Simply, you get olivine, which at addition of water gets serpentinized, and that can lead to the generation of magnetite and free hydrogen, which is quite important for this system to provide the highly reducing environment that keeps us in the Awaruite field. Nickel, again, probably most of you know, olivine in ultramafics tends to run 0.2 to 0.25 or even higher in nickel. It's locked in the olivine lattice, and it's there to stay. During serpentinization, and on the lower equation here, I've put nickel in the equation as well. You wouldn't normally put it in. It's not a stoichiometric mineral. It's a trace mineral, but need needed to show that under the oxygen and sulfur fugacity range and the temperature range outlined earlier, when the olivine breaks down and the serpentine's formed, where's the nickel going to go? It's got to go somewhere. And a lot of times it just goes into the serpentine. So you've got, if you had 0.22 nickel before, you've still got 0.22 nickel. It's, the bulk chemistry has not changed. Under the conditions I have defined, though, it will go into a Awaruite. When it does that, again, the bulk composition has not changed. And the distance that the nickel has moved is only a millimeter or two. It's not like it's in a active hydrothermal system or not in a classical Sudbury style nickel sulfide system where you get settling. This is a deposit that's generated by simple temperature change, and the only bulk change of composition that you have is the addition of water, which tends to dilute the whole thing. So here's a couple of pictures of what it looks like. You can see the centimeter and millimeter bars there. I don't know how well it shows up in this light, but hopefully you can see it. That's only at the top there. It's just partially serpentinized dunite, and at the bottom there, it's more heavily serpentinized peridotite. But those are very classic slides of the occurrence. We can stay in that kind of stuff for 200, 300, 400 meters with very, very little change. It's some of the most boring logging that you'll ever do. And we have a process for estimating the size of those and guessing what how much it is there, and with time and getting the assays back, getting your eye in, you can actually get reasonably good at it, because it's classic. You hand someone one of these pieces and you ask them, what the percent of Awaruite is, and 9 people out of 10 will overestimate by a factor of 5 or 10. Yeah, it's hard to get your eye in, but once you get used to it, you can do it. So, in some ways, this is very easy to work on. You don't have to wait to get your gold assays back. You can take a reasonable stab as to what the grade is. This is just a couple of photomicrographs. The ones on the left are much more common. The one on the right is a bit of an oddball. Petrologists always prefer to look at the oddballs rather than the common ones. So put that in there. The Awaruite, it averages around 100 microns, so not that big. It will go down to almost zero. The upper end is about 400, but the median size range is around about 100 microns, which ends up having important considerations from metallurgical recovery. So this is microprobe analysis. I showed you in the first slide, four different occurrences. This is from 3 of them. The nickel average is pretty close to the stoichiometric value of 75%, which most of the rest being iron, and then cobalt and copper both running about a percent. And there wasn't a whole lot of variation in that. This is all all the same slide. The one at the bottom left is maybe a good one to look at first, where you can see what the Awaruite looks like and pick out the magnetite. And then at the bottom here is chromite, there and there. It's actually a ferrichromite, and that is not uncommon to get along with the Awaruite. And the plain light gives you just an idea of what it looks like, and the cross nickels, you can certainly see the serpentine texture very well, and the whole view there is just 2 millimeters. So the characteristics of Decar in particular is very low in sulfur, very low in chlorine. So the thought is that the water of serpentinization was not seawater, and also was certainly not a typical hydrothermal solution. Elements like you find in hydrothermal solutions, carbonated zinc, arsenic, antimony, mercury, are absent. So there's no magmatic component. Our thought is that it's clean continental or meteoric water, and that there had to be fairly prolonged events. And when you look at as I showed you earlier on the Cache Creek terrain, it was actually being moved over a long time. So there was certainly ample period in there. Actually, it'd be neat to get some whatever minerals we can get from there, to get some age dates and send them down here, because we don't have good age dating on what the age of mineralization is. Fresh peridiotites run SG of about 3.3. We do SG on all the core samples, and they average out about 2.7. So you've had to 10 to 15% water added, and a volume increase in the order of 20%, which may have helped open up and help with the porosity. The heat source, as I mentioned earlier, it is almost certainly the exothermic reaction of serpentinization with maybe some component of a regional metamorphism. So looking at the location, Prince George here, so that diagram I showed you there, that's the sort of the center line of BC. Decar's there. The red dots are other operating mines in that area. In particular, Mount Milligan is a classical porphyry copper with some gold. It went into production about 4 years ago. It's been a great help to us, because the First Nations in this area have a very good idea what a bulk tonnage open pit mine looks like. In fact, quite a number of them from the band where we're working have worked at Mount Milligan. We mobilize out of Fort St. James, and so does Mount Milligan. That is a rail line that goes within 5K of the Baptiste deposit, and there's a major power grid along this line here. So we have a pretty good logistical area to work in. Back to this diagram that you saw before, just to remind you, and the rail line is marked there, but it's largely covered by the legend. So, how'd you explore for this stuff? There's no sulfides, so there's no gossan. There was no hydrothermal activity. So there's no alteration halo. Useless to analyze for total nickel, like with by any method, because the nickel content hasn't changed. It's 0.22 everywhere. We got several trillion tons of 0.22, but only a fraction of that has nickel in this nickel iron alloy form. It's also, as I indicated earlier, fine grained. When you get it in a cut specimen like that in the right light, it's pretty easy. But even then, if you've not seen Awaruite before, you're not going to really know if it's a sulfide or not. It takes a while to get your eye in. It's cubic, which can help. But in many places in the world, the Awaruite is associated with sulfides. It's very magnetic, like I said, but there's way more magnetite, and it isn't a one-to-one association by any means. In fact, it can be a sort of antipathetic association, plus or minus 4% magnetite and plus or minus 0.15 to 2% Awaruite. So how'd you find this stuff? Why wasn't it found before? Why has no one else ever tried to mine this? Come on, there's a whole pile of brain power here.
You mentioned the SG contrast.
Yeah.
So from a gravity survey point of view, that could be helpful in outlining the area, depending on.
Yeah,
whether you identify the Awaruite to begin with, that's not matter.
it's pretty subtle. And we've tried magnetics. We've done ground and airborne pretty detailed survey to see if that would help us. So, do you want to know how we found it? We tripped over it. We actually went to look for a gold occurrence that was right on the edge of the ultramafic listenite occurrence. A lady geologist I knew had it, and Ron and I went and had a look at it, and quickly decided it was too small and not of a lot of interest. And Ursula, that was her name, said, "Well, if you don't like my gold deposit, how would you like my stainless steel deposit?" And sort of, thought, that's a bit odd. And said, "What are you talking about?" And she said, "Well, there's a Awaruite here." We said, "There's what?" And she said, "There's a Awaruite." And she pulled out 3 or 4 pages of a thesis that was done at Carleton, a PhD, where he just mapped the ophiolite, and in thin section had mapped Awaruite over about 3 kilometers. And both Ron and I looked at each other because we both had a lot of experience in bulk tonnage open pit as well as the smaller underground. It sure got size. And the way it's detailed here, it looks like it has continuity. So we actually took some samples. We did some quick and dirty work. It was Awaruite. You could easily concentrate it in the magnetic fraction, and you could upgrade it with gravity. Huge losses along the way. We looked in the literature to see, well, how many Awaruite mines are there around the world that we've never heard of? And there's none. No one has ever tried to put this into production. So this is just this is the Sydney deposit. It's up above the tree line. I'm guessing no one here would get very excited about that outcrop. That there's a closer look at one. you wouldn't even take a sample, and you sure as hell wouldn't submit it for an analysis. Baptiste is largely covered with till. This is the till. It's running average grade. No distinguishing features from perfectly barren till. So then, that's nice, but how'd you assay for it? You can't do total nickel. You can't distinguish the nickel in the Awaruite versus the nickel in any other phase, and in particularly in the serpentine. This took us a fair while to sort of really get on top of, but like a lot of things, when you start talking to different people, Davis tube separation and recovery is reasonably common in the iron ore industry. They have a problem with their magnetite deposits. They don't want to know the total iron content. They want to know the amount of iron that's there as magnetite, because that's what they're going to recover. And so here we have exactly the same thing. We don't want to know the total nickel. I can tell you what it is. I mean, for the few thousand samples, it's between 0.2 and 0.24. But can't tell you what the percent of Awaruite. So our standard way of assaying it, as described here, it's a standard method for the iron ore industry. And on the figures I'm going to show you later, you'll always see DTR or Davis tube recoverable nickel as opposed to total nickel. For separation then, the first phase can be magnetic separation, but you'll get way more magnetite than Awaruite. So you now have to separate the Awaruite from the magnetite in some way. Data I'll show you very shortly. The magnetic separation was followed up by gravity. This Awaruite is quite fine-grained, so gravity, even using a Falcon, if any of you are used to that, a high-speed centrifugal system, still doesn't get all the Awaruite. So we've now working on other methods. We have some great work going on. We should have the conclusions we can announce in the next two or 3 months. A combination of UBC and ALS, which is a commercial lab. So UBC is doing some great work on really understanding the mineralogy, what affects it. And so we're looking at both flotation. Flotation is a very standard method for copper. No one's ever used it for nickel because it doesn't work too well for nickel sulfides. But this isn't nickel sulfide. It's different. And you can actually dissolve it quite easily as well, and put it in solution and take it out by various means. So that's we're just at a turning point there. Looking at the physical properties, there's the Baptiste deposit is there. Target B and Sydney are here. Van is over down the other side. You can't see it there. Give you an idea of the topography. We are just on the inboard side of the coast range, so just on the edge of the interior plateau, which is good. Most of the snow falls on the other side, where you can get multiple meters of snow in some of the operating mines there, and we're down to more like the snow level you guys get here. That's just a bit of a closer look. The red lines are the outer limits of the known mineralization at Baptiste. This is a bit more detail of what I showed you before. So Baptiste down here, 30,000 meters of drilling, averages a 0.118 DTR nickel. There's a 2013 we did a preliminary economic analysis. That was the pit. The mineralization was known. Well, it's stopped there. Some of our best grades were right there. So we've since drilled that off. Up here at Sid, we've only got 2 holes, 320 meters apart. One's 282 meters of 0.14, 163 meters of 0.16. Just one hole here, 1.7 kilometers from there. Again, 250 meters of 0.13. Very viable targets. Then, in 13, we only knew of a occurrence here. That was in a valley. Since then, it's been logged, and we've found quite a number of outcrops there, which over a big area with values up to 0.116 DTR. If we'd had that data at the same time we decided to focus on your drilling here, and any of you been in this exploration business, you're confronted with some really major decisions as to what you do that can result in success or failure. And one of the decisions you face when you're doing surface mapping, you like to get outside the system. You like to map everything you can. Find out what's there. It's relatively cheap. But as soon as you start to drill, you're focused. You all of a sudden are spending much more money in a much smaller area. So, do you put half a dozen holes in each one of those? And were they the best holes, or were they poor holes, or do you focus? Our partner at that time was Cliffs Natural Resources. Cliffs, a major iron ore company. They had a brief foray into looking at chrome and nickel. The chrome didn't work out very well for them, so they withdrew back to Cleveland and abandoned Canada. So we actually got the deposit back 100%. So, oops, I keep doing that. Baptiste is where we have by far the most information, but we don't know if that's the best target in there or not. And the fact of the matter of it is, it's very hard to generate the money to go out and test those. So, like it or not, Baptiste is what we are focused on. So, very briefly, within that pit, a billion tons, very low strip ratio, huge mine. We're looking at 114,000 tons a day. I mean, that's a world-class sized open pit. But mine life is not a concern here. I mean, we just haven't finished drilling out the pit, because once you got 20, 25 years of mine life, there's no economic value to the rest of it. You can find that when the mine's operating. 0.118 DTR nickel, 82% recovery. So from the magnetic concentrate. So when we use gravity, we're only getting 82% of what was in the magnetic fraction. average annual production was 82 million pounds into a con of just over 13%. And this study assumed that they were going to get a value of $7 a pound for the nickel, which was based on the price of nickel N, which was like $9.30 times, if you sent it to a smelter, you'd only get about 75% of the value. We know now that you don't have to send it to a smelter, but that's a whole evolving story. Looking at the 2013 PEA, the average cost of production, that's just the cash cost, was about $3.23, which is well down there compared to operating mines. Rule of thumb, you want a sustained value for nickel of twice your cash cost. So, we want about $7 nickel, and right now it's $5, and it's been depressed for 6 or 7 years. Nickel got way overbuilt in the last super cycle. The warehouses were just bulging. They've now been drawn down a long way, but we still have to be patient, and for probably another couple of years. The good news is that during that period, you have time. So we don't have much money, but we do have time. And that allows us to work, in our case, with UBC, but it allows us to work with people like that, understand the science a lot better, understand the fundamental building blocks well. And from that, you can build a more robust mine and do much better metallurgy. So you then take those data and you take it to a commercial lab, and you move from the test tubes stage to a reasonable size stage, and then onto a pilot plant. So in our case, ALS, a very well established, one of the best in the world in metallurgical labs, works very closely with the professors and a couple of PhD students to get the information across that boundary. Very briefly, this was the circuit that was known at that time: coarse crush, magnetic separation. You can get rid of about 75% of your material right there. Finer crush and then gravity, leading to that 13.5% nickel concentrate, which will have some chrome in it, because the ferrochromite tends to be magnetic as well. So going back to the pit outline here, I mentioned before, that was the 13 pit outlined. Some of these really good holes didn't get into the pit because of they're sloped or dip at 55 degrees, which wasn't far off the angle of the pit, so they just didn't make it in. We've since done some more drilling there, and they come up. So within that pink zone, and I won't comment on most of these, but we're getting in intersections in the hundreds of meters. Where they're short, it tends to be because they started outside the zone to get down deeper. Every single hole in here finished in mineralization. We haven't found the bottom of it yet. Inverted magnetics indicated something like 5-6 kilometers from top to bottom, and we've only hit, starting from the top up at Sydney to lowest drill hole, a maximum of 3 kilometers, in that whole range. and so you can see just eyeballing this that a lot of those holes have quite a bit better grade than the .118 that the PEA was based on. So just on 2 billion tons, both categories of nickel. For those of you who know how this works, it's very nice. A vast majority is indicated because you can put it in a 43101 PEA and a pre-fees. We're using a cutoff grade of 0.06, which gives us a life of mine of 0.115, about what we got before, but this was based on a much lower nickel price. So it was based on, I don't know if you can see the bottom here, but it was based on $6 a pound versus $9.40 a pound. So quite a bit tighter. This is a color map, and the red, of course, is the higher grade, and you can see quite clearly now that this area near surface is by far the best grade, which is nice, because what we discovered is when you do a long section, unfortunately, it's upside down. The best mineralization is down at the bottom here, except for that zone, which at 120,000 tons a day gives us about 5 years of production at significantly higher grade, which is very important. Just to put this in context from an economic point of view, so dollars per ton operating cost up the x-axis here, and Baptiste is right down there. Call capital cost capacity. So how much does it cost per ton of throughput to build this? You know, we're talking about a mine that's going to be about $2 billion. So it's big, but the cost of capital compared to the ton of ore is actually right down there. Baptiste is one of the certainly 5 largest undeveloped nickel mines in the world, and sits in a very solid position. So certainly my hope is when the next round comes to build new nickel mines, Baptiste will be near the top. And I'll just mention one other thing in passing. These are very high magnesium tailings. Magnesium plus CO2 makes magnesium carbonate. It's a naturally occurring mineral. Greg Dippel, a prof at UBC, have been working on this mainly in Western Australia for about 10 years, studying how this works. And all you got to do is just spread your tailings around, and it will capture a certain amount of this CO2. It depends what form the CO2 is in. If it's as brucite, it's much more labile, or will grab the oxygen much more readily. We've been working on this for a couple of years now, starting to get some decent quantitative figures out of it. It looks very likely that if we do nothing more than just spread our tailings around, we will sequester the amount of CO2 we produce from the haul trucks and other stuff like that, assuming that the mill itself is on hydro, which it almost certainly will be. And the other thing we're starting to investigate is when you do this, what happens to your tailings? Does it make it more stable? We know from experiments, you can take some of our tailings, you can put them in a column like shown on the right here. You can bubble flue gas through that for a couple of weeks, and you will have high-grade cement. There's no way, that's going to happen in an operating mine, but will it give you a significant advantage? So, just in closing, we call this a district because we truly believe it is. That's a big area with one well-known target and three others that we don't know whether they're better or worse. So, any questions?
Thanks a lot, Peter, for a very interesting, broad spectrum review of these. It's very interesting because I was going through some nickel resources and nickel prices in my class this morning. So they're noting the mistakes I made. Questions for Peter? Okay, we're going to go with Mark first.
What's the primary structural control, or is there any control in their elevation?
We think there, if you saw the sort of pit outline and shown a Baptiste, it is along a major structural weakness. But boy, when you are looking at the core or you're looking at the outcrop, you don't really see that. It's very subtle. But we think that during subduction that there was a strain that caused that fabric to develop, and we think it was very important to give us the volume that we wouldn't have otherwise got.
And then you have groundwater down, and then
Well, we think it is meteoric water, and that it could have been done where the ultralight is quite a bit deeper than it is now. I mean, it comes to surface now. It could have been down a kilometer or two at that time.
Tom?
What's the drill spacing at now, Peter? I lost track of where we were with the resources.
Yeah,
But presuming most of it's indicated,
yeah.
what's the drill spacing, average drill spacing for that?
The drill spacing is roughly 200 meters, and the variogram range is 400 meters. This looks a lot like an iron ore deposit. It's more homogeneous, it goes on longer, more continuous, little variation than any porphyry copper I've worked on. If you think iron ore deposit, that's much more like what it looks like.
But the distribution of the ROI, within the magnetite,
Yeah.
is that fairly constant?
Yep.
Okay.
Yeah. The changes are quite slow.
Dallas?
When you're marketing the concentrate, you said you wouldn't necessarily be selling it to a smelter. Would you be competing with some of these nickel laterite oxide or direct shipping oxide material from, say, the Philippines or Indonesia, where they have a couple of percent or half a percent and a half nickel and maybe a lot of iron anyway, which is directly used in the stainless steel making process.
No, that is a really good question that we've investigated a lot. So, what you're referring to is commonly called pig nickel, because the Chinese just took it and they stuck it into a pig iron furnace. And yeah, 2% is at the high range, but there's certainly lots at one and a bit. It has certain problems. You can't concentrate it. You got to deal with the whole thing. It's got a high water content, so it uses up a lot of energy. But yeah, it's probably the most direct competitor with what we're going to do. So we got a couple of options with Arcon. We've talked to 6 different steel producers, 3 in Japan, 1 in Korea, and 2 in China. They all say, based on where we are now, yeah, we like it, send us some more, and our indicated price is that we'll pay you, I think the low was like 78% of LME and the high was like 95%. And so at one level, they're going to put it directly into a stainless steel furnace. At the other level, they were going to put it in a kiln and make classical 40-50% ferro nickel. With the work we're doing now, and we can't talk in any detail about it yet, unfortunately, we're looking at concentrations a lot higher grade, which will almost certainly go just directly into a stainless steel furnace.
Cliff, and then I'll go on.
Have you looked at the BGE contents of the Awaruite? 0?
Yeah. No, nothing. I mean, you can maybe find a ppm here and there, but no, there is none. And so if you think about it, an ultramafic, a barren ultramafic, doesn't have any PEs in it. And so the solution that came in here, wasn't carrying any. So there wasn't any before, there's none now.
Ron?
Peter, could you tell us a bit about your company, FBX Nickel, and junior companies raising money, markets, and all that kind of stuff?
So do you want the sad story or the happy story?
I think I figured out what the sad story is. Maybe you just,
Okay, well, in this case,
reality of a
yeah,
junior,
junior. I mean, like you, I've been through this iteration several times. This particular one, I'm really enjoying, but when you're the first in the world to do something, you get a huge amount of skepticism. And when we first mapped it at surface, we're a broke junior and we can only afford to do surface work. We needed to find money. Very hard to find it on the street. So actually, timing was great. Cliff's had a new president. The new president said, gee whiz, guys, we've mined iron ore for 100 years. We've sold it to steel mills. Steel mills buy other things. They buy chrome and nickel. Go out and find some. So they had a geological team, and the team said, we're not going to go after oxide nickel. Those are $5 billion chemical factories, and everyone that's been built has lost money. Nickel sulfide hasn't been found forever. The last one was Voisey's Bay of any size. And then they tripped over this thing that they were marketing and really loved it. They only made a commitment to spend $1 million on it. They could have withdrawn. So they just went and drilled three holes, and they were looking good. So then, over the next 5 years, under the terms of the agreement, they produced a PEA after spending about $22 million US. And so that's how we probably only spent about $500,000 on it with our surface work at the start. So that's how we got it funded. But then Cliffs had earned 60%. They pulled out of Canada, and they're sitting there with 60. What the hell can we do with 40%? So we actually bought it back from them for $4.5 million. So they put 22 US in it. We brought it back for 4.5, but we've had to borrow that. And so we're sitting there with a substantial debt to repay. And, so we're hoping two things. A, that the metallurgy will be very, very compelling. And I'm certainly got a lot more confident about that. And that the price of nickel will go up, and we'll be able to get the next round of funding. But my other fear is, we're trading at 15 cents. We got a market capitalization of $8 million. Someone who likes the story could come along with 16 million and buy us tomorrow. And I think it's worth a hell of a lot more than that. But that is the life of a junior company. So any of you who have had or are heading in this direction, how you finance something is, and without blowing your brains out or having 500 million shares out and trading at a penny, is a challenge.
Thanks, Ron, and thanks, Peter. We'll cut the questions off. We'll take them offline. So thanks again, and Tom.
Well, I think the CIM Foundation did a really good job finding you. And I think the Hall of Fame did a really good job finding you. Congratulations. And on behalf of the local CIM, and of course our friends at UNB, would like to give you this parting gift in case you want to continue your dreams. This is a really nice...
Trials and tribulations of early mining. No trials and triumphs. I like the triumphs part.
So all you have to do now is find out what to do with the tailings. You spent $6 a ton making them.
Yeah.
I hope that you can find some value that's attached to them.
You have hit on our current Achilles heel. So we found it. We did the exploration. We got the grade in tons. The metallurgy is pretty well done. The tailings is exactly. But we have a big crew at UBC working on that. So hopefully they're a lot smarter than me. Oh.